Bismillah ar-Rahman ar-Rahim. I hope everybody is okay. Our lecture today about differential derivative and gradient factors. Suppose we have a differentiable function fxy. We know that we can compute the rate of change with respect to t along the differentiable curve, where x is given by tt and y given by ht. The rate of change, as we know, is given by df dt equal partial f partial x dx dt plus partial f partial y dy dt. At any initial point p naught, if we substitute in the above function, we get the rate of change of f with respect to increasing t. Now, suppose the function f of x and y is defined throughout the region R in xy plane. That's a point p naught of x naught and y naught is a point in R, and that u equal u1i plus u2j is a unit vector. Then the equations x equal x naught plus su1 and y equal y naught plus su2 parameterize the line through p naught parallel to u, where define the rate of change of fxy as follows. Now, let us consider the following definition. The first derivative of the function f of x and y at a point p naught in the direction of the unit vector u, which equal u1i plus u2j, is the number below. The first derivative of f with respect to t at u p naught equal the limit when s tends to 0 of fx naught plus su1, y plus su2 negative minus fx naught y naught divided by s. If the limit exists, the direction derivative defined above is also denoted by capital Du of f at p naught. Now let's consider the example 1. Using the definition, find the derivative of f of x and y equal x squared plus xy at the point p naught 1 and 2 in the direction of the unit vectors given below, u equal 1 divided square root of 2 times I plus 1 divided square root of 2 times j. Apply the definitions. The first derivative for the function f with respect to t at u and p naught at the limit when s tends to 0 for the function when substituted by x naught plus su1 and y naught plus su2 minus the f at x naught and y naught divided by s. Substituting by the value of u and the value of the point p naught 1 and 2 and simplify, we can get the final result as 5 divided square root. The dot product, if we have two vectors, a row vector u and a column vector v of the same length, we know that the product of the two vectors give us a scalars, which we call it dot product, as follows: u times f equals summation from I equal 1 to k ui times vi. So if k equal 2, then we can simply find that u times v equal u1 times v1 plus u2 times v2. Considering the graph below, array U and array V having an angle in between theta, then we can find out that U times V, which is equal U1 V1 plus U2 V2, can be written as the absolute value of U times the absolute value of V cosine theta. Before we proceed, let's recall our previous information about the unit vectors. A vector V of length 1 is called unit vectors, and the standard unit vectors are of 3 items: I, which I1, 0, 0, J is 0, 1, 0, and K is 0, 0, 1. Any vector V can be written as a linear combination of standard unit vector as follows, where V equal V1, V2, and V3, substituting by the above notations, then we can get V1, 0, 0, plus 0, V2, 0, and at the end, the last item 0, 0, V3. So, which we can substitute it as the final result, V1I plus V2J plus V3K. For any differentiable function fx and y, where x equal x0 plus su1 and y equal y0 plus su2, we can find the first derivative of f with respect to s at u p0 equal partial f partial x at p0 times dx ds plus partial f partial y at p0 times dy ds simply can be written as partial f partial x at p0 times u1 plus partial f partial y at p0 u2, and can at the end be written as two product partial f partial x p0 times I plus partial f partial y at p0 times j times u1 I plus u2 j. The term partial f partial x at p0 I plus partial f partial y at p0 j is called the gradient vector of f, x, and y, and also denoted by the reciprocal triangle f. And u1i plus u2j is the direction u. Therefore, the first derivative of f with respect to s at u p0 is the gradient f times u. Now, let us consider the following example. Find the first derivative of the function given by x e to the power y plus cosine xy in the direction of v equal 3i minus 4j. The direction of v is the unit vector obtained by dividing v by its length. We know we can compute the length by the square root of 3 to the power 2 plus 4 to the power 2, which is 5. So u equal v divided by absolute value of v equals 3 divided by 5 times I minus 4 divided by 5 times j. The partial derivative of f are everywhere continuous and at 2 and 0 point are given by partial first derivative of x at 2 and 0 equal e to the power y minus y sine x y. Substituting by 2 and 0 we get 1. And the first derivative of f with respect to y at 2 and 0 is given by x e to the power y minus x sine xy. Substituting by the point 2 and 0, we get a 2. So the gradient of f at the point 2, 0 is gradient f computed at 2, 0 times u equal first derivative of f with respect to x at 2, 0 times I plus first derivative of f with respect to y at 2 and 0 times j equal I plus 2j. So the direction of f at the point 2 and 0 equal the gradient of f at the point 2, 0 times u, which can be simplified as follow: I plus 2j multiplied by 3 divided 5 times I minus 4 divided 5 times j. We can simply get 3 divided 5 minus 8 divided 5, which is -1. Also, we can evaluating the dot product in the formula direction f equal absolute value of gradient f times the absolute value of u cosine theta, which simply the gradient f, the absolute value of gradient f cosine theta, where theta is the angle between the vectors u and gradient f. Properties of the direction derivative. The function f increases most rapidly when cosine theta equals 1 or when theta equals 0. And u is the direction of gradient f. It means that at each point p in its domain, f increases most rapidly in the direction of the gradient vector, and the derivative in that case equal absolute value gradient f cosine theta equal the absolute value of gradient f. In the same manner, f decreases most rapidly in the direction of negative the gradient f, and the direction is the same like above but with negative sign. At any direction u or signal to the gradient f not equal 0 is the direction of 0 change in f, because theta in that case equal pi divided 2 or 90 degrees. And in that case the direction f equal 0. Now let's apply these properties in the following example. Find the direction in which f of x and y equal x squared divided 2 plus y squared divided 2. A increases most rapidly at the point 1, 1, decreases most rapidly at the point 1, 1. C. What are the direction of 0 change in f at the point 1, 1? For point A, the function increases most rapidly in the direction of gradient f at 1, 1. Let's say gradient f computed at 1, 1 equal xi plus yj computed at 1, 1, and its direction u equal at the end 1 divided square root of I plus 1 divided square root of j. Similar, for point B, the function decreases most rapidly in the direction of the negative of the above result. Finally, for point C, the directions of 0 change at point 1, 1 are the directions orthogonal to gradient f, which are n equal negative 1 divided square root of 2 times I plus 1 divided square root of 2 times j, and negative n equal negative 1 divided square root of 2 times I minus 1 divided square root of 2 times j. Thank you for this.